In this video, I want to take a look at tangent planes to surfaces. And before I do, though, I just want to point out that for the next few weeks, this course is going to look a lot like a Calc 1 course. The same topics, think about the applications we did for the derivative at the end of Calc 1. We did, tangent lines, we did linear approximations, differentials, we did max-mins problems, we did related rate problems, all those things we do again, but with more variables. It's the nature of Calc 3. So, and you're gonna think I sound like a broken record every time I say, remember back in Calc 1? Well, let's go. Remember back in Calc 1 when we used the derivative of a function to find a tangent line to the graph of that function, right, at a particular point. We want to do the same thing now with functions of two variables, except that rather than a tangent line, we'll be coming up with a tangent plane. Okay, so I'm going to talk about this both in general and specifically. That is, I will be working in general for things that are up against the left column, and then there'll be a picture and the calculations for that particular function over here indented to the right a bit. So here we go. We're going to start with the function, z equals f of xy, and the point x0, y0 that is in the domain of the function, actually in the interior of the domain. I want a little bit of space around it so that other points are also in there. And then I want to consider two vector functions, right? So these are just curves now in space. And although I didn't put the little vector hats over the r's, they are vectors here. So r1 of t is going to be x0 plus t, comma, y0, comma, f of x0 plus t, comma, y0. So what I'm doing is I'm describing, if you didn't have the z-coordinate, this would just be a line parallel to the x-axis passing through x0, y0. Right? Only the first component is changing as t changes. The y0 just stays constant y0. But then when you plug those points into f to get the z, what you're doing is you're describing a curve along the surface. So in my particular example here, I've got the function f of xy equals 2 minus x squared over 2 minus y squared over 2. So this is an upside down paraboloid shifted up 2. And the point that I'm going to be interested in is the point 1, comma 2. If you plug that in, you get like 1.5 or something, or well, let's try it. 2 minus a half minus 2. So this is negative half for the z value here. R1 of t here is 1 plus t, comma 2, comma, plug all that stuff in, right, with the t's plugged in like this. And what that's describing is this curve that you can see highlighted here passing through that point. That's 1 comma 2 comma minus a half. So it's, no, that's moving, no, it's this one. This is the one moving in the x direction, right? And then R2 is a similar thing, only it moves only in the y direction. Right? So it moves just that way, and that's this one. The x-coordinate stays 1 all the time, and the y-coordinate changes. Right? The way I have this set up is I have it set up so that when t is 0, you are at the point in both curves, you're at the point 1 comma 2, and then the z value would be negative half. Right? So t equals 0 in both curves corresponds to the point that we're interested here. Okay, that's why I set it up that way. Now, consider the two derivatives of these vector functions. Right? The derivative of a vector function we saw earlier in this course is tangent to the curve described by that vector function. So taking the, let me see if I can see this, taking the derivative, this is with respect to t now, so this is just, that's a constant plus 1, and this is just a constant, so the derivative is 0, and then here, this is taking the derivative with respect to t, but the t is just changing the x component. This is just like taking the partial derivative with respect to x, right? Only it's the t playing the role of x here, but it's in the x component that things are changing. So this is just well, 1, 0, and this is just the partial of f with respect to x. Right? Now you could say, well, there must be a chain rule where you take the derivative of the inside, and it's like, well, yeah, there is a chain rule, but the derivative of the inside is just 1. Right? So this is just the partial with respect to x. And likewise here, where you're changing just in the y direction, derivative with respect to t here is 0, derivative with respect to t there is 1, derivative with respect to t here is the partial of f with respect to y, because that's the part that's changing. Right? So this is the partial with respect to y. So let's do that for our, before we do. And notice if you plug in t equals 0, that the derivative at t equals 0 is, you plug a 0 in for t here and a 0 in for t here, you're just evaluating the partial derivative either with respect to x or with respect to y at the point x0, y0. So these are tangent vectors to those curves that we just saw. And so let's do that now with our example. So remember, what was our function? All right, remember our function here was this. So the partial with respect to x is just, well, that would be negative 2x divided by 2, so just negative x. And likewise, the partial with respect to y here would be negative y. Partial with respect to x is negative x, but the x was 1 plus t, and the partial with respect to y was negative y, right, these things. And the y was 2 plus t. Those were the y values I was using. Plugging in t equals 0, we get just minus 1 and minus 2 here. And that should be a 1. Hang on. So these two vectors are the vectors that are tangent. You can see them drawn here in yellow to both of the two curves. Now I can actually see this in rotated around if I click on it here. So you can see that each of those vectors is a tangent vector to the curve. There's one of them. There's the other. And so not only are they tangent vectors to their respective curves, they are tangent vectors to the surface at that point. And I can use those two vectors now to generate a plane. And that plane will be my tangent plane. So let's do that. Okay. Now, remember, how do we come up with the equation of a plane? I need a point that it goes through, and I need a normal vector, right? Perpendicular vector. So I have a point that it goes through, x0, y0, f of x0, y0, right? That's the point on the surface. Now I just need to know a normal vector. But I have two parallel vectors, so those two parallel vectors, I can take the cross product to get a vector perpendicular to them. And now I can take the cross product in either order, and it'll be fine. I happen to do it in this order because I know what answer I want. Okay? The difference in the order is just a matter of whether it's pointing this way or that way. Right? It's just a minus sign on everything. But I particularly want this to come up with positives here and a negative there, rather than the other way around. So I'm doing R2 prime crossed with R1 prime, just your standard cross product. And you can see in the first component, it's going to be just the partial with respect to x here, minus 0. That's this one. And then in the second component, remember you do the second component backwards, so we multiply by minus 1. So anyway, it's this minus that to get partial with respect to y. And then the last one here is just negative 1. Okay. So the normal vector for the tangent plane has components partial with respect to x, partial with respect to y, negative 1. And you don't have to do this every time. You don't have to do this cross product every time because you know the result's always going to be the same. That at the point x0, y0, the normal for your tangent plane is going to be components of partial with respect to x, partial with respect to y, minus 1. And those partials are evaluated at the point you're interested in. So I can write down the equation of the plane as such, right? This is the x component of my normal vector times x minus the point that I wanted to go through. The y component of my normal vector times y minus the y component of what I want the plane to go through. And then the z component of the normal vector, -1, times z minus the z coordinate of the point I want it to go through. And I'm going to just rewrite this by solving for z here. So I'll distribute this -1 in and then bring the z to the other side of the equation. All right. So z is f of x0, y0, so that's the point on the surface, plus this linear equation. Right? I say linear because it's just x to the first power and y to the first power multiplied by constants added up. Right? These are constants. This is not x, y. This is x0, y0. Likewise here, this is x0, y0. You're plugging those into the partial derivatives to come up with a number. So in the example we had here, the partial with respect to x was -1 and the partial with respect to y was -2. And the function value was -1/2. So I have z equals -1/2 minus the quantity x minus 1 minus 2 times the quantity y minus 2. And this is my tangent plane. And this is the graph of it right here, this purple thing. I should point out that it looks kind of funny around the point that I'm interested in. And the reason it looks funny is because the software, the computer, is having a tough time deciding what to draw on top of what. That is, the surface and the plane are so close to being the same thing at that point that it can't tell which one to draw on top of the other. But if I look at this from the side here, you can see that that plane is definitely a tangent plane to the surface. Right? It hits it just at one point. Now, I have to be careful when I say that because the definition of a tangent plane isn't a plane that hits it at one point. Because some tangent planes hit at more than one point, and there are some conditions where you have planes that hit at one point, but you wouldn't call them a tangent plane. Just like think about the absolute value function, right? When in Calc 1, at that point at 0 where the sharp corner is, do you have a tangent plane? I mean, in a way, you have a lot of tangent. Sorry, you don't have tangent plane. You have tangent lines. You have a lot of tangent lines because a lot of them that just hit at that one point. But there isn't one that you would say, "Oh, this is the tangent line," because it's got the right slope. Because there isn't even a slope there. Right? So anyway, same thing here. Is that I'm not going to define this as the plane that hits at just one point. I'm going to define it as the plane determined by those two vectors, by those two tangent vectors to those two curves in just the x direction and just the y direction. So here's what we ended up with. Here's the equation for the tangent plane that we just got. Z equals function value plus partial with respect to x. I'm also changing my notation here just because you'll see it written this way quite a bit. So partial with respect to x evaluated at x0, y0. Times the quantity x minus x0 plus the partial with respect to y evaluated at x0, y0 times the quantity y minus y0. So compare that to what we had in Calc 1 for the equation of a tangent line to the graph y equals f of x at x equals x0 is y equals f of x0 plus the derivative at x0 times x minus x0. This looks very much the same. Some function value plus the derivative times a change in x. Now we have a function value plus the derivative in the x direction times a change in x, plus the derivative of the y direction times a change in y. Okay? Tangent line from Calc 1, tangent plane from Calc 3. Okay? Let's do one more example here. So I've got this function, z equals x squared minus 4xy plus y squared, and the point I'm going to be interested in is the point 1, 0. Evaluating the function at the point 1, 0, I just plug a 1 in and a 0 in, and I get 1. So the height is 1. The partial with respect to x of this thing is 2x minus 4y plus 0, and the partial with respect to y would be 0 minus 4x plus 2y. Plugging in the point I'm interested in, so the partial with respect to x evaluated at 1, 0 is 2 times 1 minus 4 times 0, which is 2, and the partial with respect to y at 1, 0 is minus 4 plus 0 is -4. So those are the two partial derivatives, 2 and 4. And now I can write down the equation. It's going to be z equals 1, that's the function value there, plus 2, that was the partial with respect to x, times x minus 1, that's the x component that we wanted to go through, minus 4, partial with respect to y, times y minus 0. 0 was the y component we wanted to go through. This is the equation of that, that tangent plane. Okay. One of the big mistakes that I see students make, they make it in Calc 1, they make it in Calc 3, is that they treat these partial derivatives not as constants. That is, they forget or neglect to plug in the x0, y0. That is, you know, in this problem, the partial of f with respect to x is 2x minus 4y. And what I'll see is, instead of a 2 being written here, they'll write 2x minus 4y, because they didn't plug in the point 1, 0. Right? I don't want just the general partial derivative. I want the partial derivative evaluated at the point you're talking about. Likewise here, the partial with respect to y, at the point you're talking about. This should be a number. This should be a number. And in this case, they're 2 and -4. Now, I did this example because this is an example where the tangent plane doesn't hit at just one point. We're talking about this point right here, and it looks like the plane is actually cutting through. This surface is a saddle that's been twisted a bit around the z-axis. Let me click on it so we can see it in 3D. There's the point I'm interested in, and you can see that blue tangent plane kind of cuts through the surface. It is tangent right at that point. Right? You can look at it there. You can see it on the back side cutting through here. And it does just barely touch. Again, the computer is having trouble figuring out which one's on top because they're so close together. That's the beauty of the tangent plane, is that it's close to the point that that you're talking about. The plane and the surface are essentially the same thing. They're really hard to tell the difference. Zoom in and you can't tell the difference because the surface gets really flat and it looks just like the tangent plane. Okay? So anyway, tangent planes don't just touch at one point, but what they do is they match the surface at the point that you're interested in. So they match the derivative in the x direction, they match the derivative in the y direction. And you get that plane. Okay. So there you go. There's tangent planes.